Let's take a look at the difference between distinguishing instantaneous quantities from average quantities. Both can be valuable in physics, but we'll find that instantaneous quantities typically tend to be more useful as we build up the fundamental ideas in physics. Let's take a look at an example. We have a ball up here starting at rest, and it's going to roll down this inclined plane. Notice I'm choosing down to be the positive x direction and up the ramp to be the negative x direction, and this ball will only move along in a straight line as it goes down the ramp here. So we're free to choose the x direction to be parallel to that, and I've also indicated that the length of the ramp, lowercase l here, is 6 meters, and the amount of time that it takes for this ball to go from the top when it's at rest all the way down to the bottom is 3 seconds. We'll ignore friction and we'll ignore any air resistance as well here. Now take a look at this claim. A student claims the instantaneous velocity of the ball is 2 meters per second at the bottom of the ramp. Is this student correct? So think about this, look at the given information, and write out what you think on a piece of paper. Will the instantaneous velocity of the ball be 2 meters per second right here at the bottom of the ramp? Make sure you have a reason why you think whatever it is you think as well. Go ahead, pause the video and try that. The answer here is no. The claim is incorrect. And the ball will speed up as it rolls down the ramp. And it's going to be traveling at different velocity values as it goes down the ramp. So here it's going pretty slow, maybe like half a meter per second, and it starts to speed up and it's going faster and faster. And maybe by the time it gets down here, it's going a lot faster than, say, 2 meters per second. I'd have to give you the physics, or you'd have to work that out to predict exactly how fast it was going down here. And we'll get there soon enough. That's not the purpose of this video. But you can reason that, it speeds up, and so it's going to be traveling at different speeds as it goes down. So if you just divide these numbers, you're always going to get 2 meters per second. If you divide 6 meters by 3 seconds, and clearly it's not going always at 2 meters per second because it speeds up. It could be that you just get lucky with the math, and if you divide the length of a ramp by some time or something, it would always give you the speed at the bottom. That doesn't end up being the case with the laws of physics. But it would be a good guess. So let's see what's going on with this difference then between instantaneous velocities and average velocities, and really how to do this properly. All right, so for these average quantities, we can calculate average speed and what's called average velocity. Let's look at average speed first. You just take the total distance that you travel and you divide that by the time interval. It's pretty easy. We'll see an example in a second. Average velocity, a little bit more subtle. What you do is you take the displacement of the object. That's different than distance traveled, remember, and you divide the displacement by the time interval. So I've shown that here with the symbol delta x, or the change in the one-dimensional position x, and we'd have a final position minus an initial position, and then just divide by the time interval during that change in position. And that would give you the average velocity. Now there's a couple things to watch out for. Let's see it with an example. So take a look at this. We've got a car, and I've indicated the position of the car right on the front wheel here with this little blue dot at 3 moments in time. So at moment 1, the clock reads 5 seconds. The car travels to the right, and at moment 2, the clock reads 10 seconds, and now the car is at a different position over here, as you can see. And then if moment 3 is later in time, of course, this car must have instantaneously turned around here. So just imagine it just kind of flips around real quick and then is now traveling backwards to the left, and it ends up at a position, or at a moment 3 at -4 meters, and the clock reads 17 seconds there. All right, so now you have all the information to see that this car goes all the way to the right and then turns around and goes to the left. Now I haven't given you any information about how fast it's going. I've just given you these positions and these clock readings. And from this, you should be able to calculate, number 1, the average speed between moments 1 and 3. So over that entire motion from 1 all the way to 3. And then number 2, calculate the average velocity between moments 1 and 3. Okay, so pause the video and see if you can do this correctly. All right, average speed, total distance over time interval. So you got to think a little bit here that this object travels from moment 1 all the way to moment 2. That's 14 meters in distance. 8 to get to 0, and then 6 more here, so that's 14, and then it turns around and travels another 10 meters in the other direction. You add those two numbers up for distance, and you end up getting 24 meters. And then the amount of time, got to be a little careful here, we got to find the time interval, so the difference between clock reading 3 and 1, so that would be 17 seconds minus 5 seconds, which would give you 12 seconds, so we get 24 meters divided by 12 seconds, and that's an easy division to do, and you get 2 meters per second. Remember, speed does not have a direction associated with it, so there you go. All right, and then for average velocity, we just apply what we learned previously, and our displacement between moments 1 and 3 is position 3 minus position 1. We do the division out. Watch out here, it's a minus the position 1, so that first position is negative 8 meters, and that'll add here, so you get 8 minus 4, and then that'll give you positive 4 divided by 12 seconds of time, and that gives you 4 divided by 12 is about a third, so there you go. So 0.33 meters per second. Now it's important to note how different these numbers are, right? We can see clearly we get 2 meters per second versus 0.33 meters per second. And in general, you won't get the same value for average speed and average velocity when you're doing the calculation. And that's simply because one of them uses distance and the other one uses displacement. And the calculation of displacement is involved with positions, which include directions associated with them. Positions can be positive and negative, and so that plays a role in the math, and it ends up giving us different numbers here. And you can see if you wanted to get an interpretation of like on average how fast was this thing going, well, it would look like average speed would kind of be a better quantity to do that for. In this case, average velocity doesn't really help us all that much. It's a number kind of close to 0, and we were going in the positive direction for a certain amount of time, and then we turned around and went in the negative direction. And so those direction changes are kind of, playing a role here. Like imagine you went like really far in the positive direction for a long time, and then you went in the negative direction just a little bit for a short amount of time, and you ended up way over in a positive position. Well, then your average velocity would be really positive. Most of the time you were moving in the positive direction with some speed. But if you're kind of equally going back and forth, you get these numbers close to 0, and they can really not provide that much meaning in terms of how fast you're going. So just watch out for that when you're reporting and understanding what the average velocity is. All right, let's wrap this video up, and hopefully you can see just from our last example that if you were to take the absolute value of the average velocity, it does not equal the average speed at all. So there would be the absolute value of 0.33. That does not equal the number 2. And I find students often come to a physics class thinking this is true. For some reason, they might have seen it before in a math class where they're taking absolute values of velocities and getting speeds. And it needs to be stated explicitly that if you take the absolute value of the velocity at some instant in time, not the average velocity, but how the velocity of an object at some exact moment in time, right? If you take the absolute value of that, and when you're working with one-dimensional motion, then that will give you the speed at some instant in time. And really all that means is, here's a car, just draw it out here. And let's say you're traveling in one dimension and you have a velocity of -3 meters per second, which means, of course, you're traveling in the negative direction. If you take the absolute value of -3 meters per second at this moment in time, then you get 3 meters per second, which would be your instantaneous speed. Okay, so watch out for that when you're working with average quantities. All right, let's take a look at one final example. Here's a view from above. We're looking at a car, and it's traveling in a circle at constant speed. And it ends up stopping where it started. So it began right here at this position, goes all the way around at some constant speed, and it ends up stopping right there. I want you to do two things. Number one, figure out the average speed. Just do this in terms of variables. So we get total distance divided by total time, or time interval, which we'll just use the variable delta t for that. But what would go here for total distance? I'll let you figure that out. You're looking at a circle. And then also calculate in variables the average speed. You have enough information, sorry, the average velocity. You have enough information to do that. And we're um, technically in 2 dimensions here, but it's going to work out to where we can just use some concepts that we've talked about. In fact, I'll write it like this. Okay, displacement over time interval. Go ahead, pause the video, and calculate the average speed and then the average velocity for both. All right, well, for average speed, I'll do that down here. And total distance for one trip around the circle, well, that's just the circumference of the circle, and it's 2 pi r. So hopefully you know that from your math class. And then the amount of time it's taken is delta t. Typically, we write that as capital T for what's called one period, which is one trip or one cycle, one complete cycle, like around a circle, or if you have a pendulum going back and forth. So I'll just leave it like that since it looks familiar to what we usually do. So that's cool. So that would work. And then what about average velocity? Well, if we start here and we end there, we have not been displaced at all. So we'd have 0 for our displacement, and we'd end up getting 0 meters per second. That's problematic because, I mean, it's correct, but it really doesn't give you any information at all about how fast you were going. So you can see how limited average velocity is in that case. All right, so that wraps it up for the video. I'll kind of leave you with this thought. If we go back to the first example with the ball rolling down an inclined plane and speeding up, you might be wondering, okay, so then how can we predict exactly the velocity of an object at some moment in time? Like right here, exactly how fast is it going? And then maybe down here, how fast is it going? Well, we'll see soon on how we can build up with what are called the equations of motion the ability to not only predict how fast and what direction something's going at any moment in time, but also exactly where that object would be located along a number line. So with that, take care, and we'll see you in the next video.